Okay, I will ask all of you to be ready with your pen and paper. And if you are sitting in front of a desktop, it would be nice if you uh, uh, open your Excel sheet. If I ask you to do something, you can quickly do it, okay, whenever it is required. And if it is required. So today I'm going to talk about something which has not been talked so far in previous discussions. And my topic is skewness and kurtosis. And we'll try to understand what do they mean with respect to some discrete data. Okay. Now, we have already known how a normal curve look like. Normal curve generally looks like this. And we all know that this curve is symmetric about this axis. So that the left-hand side of the curve, the left-hand side of this vertical bar, if we consider this to be our fx, is having the same amount of area as that of its right-hand side. Okay, and that the mean and median and mode of the curve always falls at the same point. So this point is the point of mean, this point is the point of median, and this point is the point of mode. Normal curve is a symmetric curve, but generally when we deal with data taken from our life, then we often do not get normal curve as we expect them to be. Rather, we may find the curve to somewhat look like this. Okay, and or it may look like this also. None of these curves are normal curves, because any layman can say that these curves are not symmetric about the vertical part. Or the curve may look like this also. So what is the difference between this curve and that curve? The difference is, in this curve, if I call this curve to be figure 1, and if I call this curve to be figure 2, in figure 1, the curve is biased towards the right-hand side. So this is the amount of bias that is happening to the curve. And in figure 2, this is the bias of the curve to the left-hand side. Amount of bias can be studied, can be measured. So in such a situation, as depicted in figure 1, the curve is called positively skewed curve, and this curve is called negatively skewed curve. Okay, and the bias, the measure of the bias that is happening to these two curves is calculated by a quantity which is called skewness. By skewness, we actually mean how much the curve is biased towards one half of the vertical part, be it the right half or be it the left half. But when it is about a normal curve, we can immediately say that normal curve is neither biased towards the positive side nor biased towards the negative side. And hence, normal curve is actually called symmetric curve. Okay, so this is the thing that we are going to discuss in our today's class. And with the help of an example, we are going to measure skewness of a given probability distribution, where we are going to consider a discrete case. Now, for calculating this skewness, we need a tool, a mathematical tool. And that tool is, which is actually known as the measure of skewness, requires some sort of prerequisite discussion of about something, some other quantities that I need to discuss first. And then I'm going to show you with an example that how to measure the skewness of the curve, or how to measure the skewness of a given data. Okay. The quantity that we need is nothing new to you, but its special case has been used several times in our class. The quantity is called moment. And there are two types of moments. Okay. One type is called the moment about the origin, which I'm going to define first of all. And another type is called moment about mean. Okay. Now, let me give you the formula for both of these two. In general, the rth moment about the origin of a random variable capital X is denoted by mu r prime. This is the notation which we'll be using, and this is the expected value of the quantity capital X when raised to the power r, or expectation of the quantity capital X of the variable capital X when raised to the power r. For discrete case, we calculate this quantity by considering the summation over all possible values of X, and we multiply X to the power r by the probability mass function fx. Okay, this is the formula A in our case. And similarly, this happens when the case is discrete. Okay, so this is for discrete case. And similarly, when the case is continuous, then this definition remains same. Only difference is we consider the integration sign rather than to use the summation sign. We integrate this quantity X to the power r fx over all possible values of X. This happens when the case is continuous. Okay. What is moment about mean? In case of moment about mean, we define it in the following manner. The rth moment about the mean of a random variable capital X is denoted by mu r. This is the notation, and it is defined as the following. It is the expected value of this quantity. We consider the difference x minus mu, we consider the difference x minus mu, and this difference is raised to the power r. You can put another bracket if you need, or you may avoid it, no problem. This is similar to expectation of x minus mu to the power r. Okay, too many brackets sometimes also create clumsiness, so we can remove the third bracket if we wish, but the basic meaning of the thing, of the expression, remains same. What is happening over here is that, you know, random variable takes various values at different points of time, and from each of these values, I'm subtracting the mean, which is mu, which is constant, and I am raising the difference to the power r. Okay, and in this actually means mathematically that we are going to calculate the quantity x minus summation x minus mu to the power r multiplied by its probability mass function. Summation is taken over all possible values of x. This is our formula B when the case is discrete. And if the case is continuous, then in a similar manner, we integrate it over all possible values of x, the same quantity x minus mu to the power r fx. And this happens when the random variable is a continuous random variable. Okay. For discrete case, however, we will consider these points r to be taking values like 0, 1, 2, ... up to infinity. This is for the discrete case. And here also, it will take values r equal to 0, 1, 2, up ... up to infinity for discrete case. And if the case is continuous, the range of x is minus infinity to x to infinity. This is for the continuous case. Here also, the range of x is from minus infinity to plus infinity, which is for the continuous case. So this is our formula. This is our prerequisite for the motivation of calculating the bias of a given probability distribution. Now, I hope that at this point, I can erase the right-hand side figure. Probably you have already copied or taken the screenshot of the page. So I'm retaining the left-hand side, the formula that I have written on the left-hand side. And for the time being, I'm going to erase the figures that I have drawn so that I can continue in this particular page. Okay. So I'm erasing these figures for the time being. Now, why am I saying that this thing is nothing new to you is because of the following fact that I'm going to explain over here. A few details about this moment about origin and moment about mean. Now, for discrete case, I'm talking. Now, let's concentrate on the discrete case first of all. Now, you see that if we choose R is equal to 0, then moment about origin, this becomes mu 0 prime, and this is nothing but expectation of x to the power 0 by definition. And this implies summation over x to the power 0 fx, which is summation over x fx. And since fx are probabilities, so total probability is 1. So for r equal to 0, we are actually getting mu 0 prime as 1. Similarly, for continuous case, if I want to calculate mu r prime at r equal to 0, this would be expectation of x to the power 0. We will consider this integration, and which is nothing but equals to integration over x fx dx, where the total probability is 1. Okay. Now, what will happen if r equal to 0 in the formula of moment about the mean? If I want to calculate moment about mean at r equal to 0, we get mu 0, and mu 0 by the formula is expectation of this quantity, which is summation over x, x minus mu to the power 0 fx, which is as before it is 1, or integration over x, x minus mu to the power 0 fx dx, which is also 1 for discrete and continuous case respectively. From this simple example, we are able to see that for r equal to 0, the value of mu 0 prime and value of mu 0, both for discrete and continuous case, are actually 1. So this is our first observation. Okay. Now we will consider another point, which is r equal to 1. And let's see what happens in that particular case. If okay, let me draw a line over here. Okay. Now, if r equal to 0, if r equal to 1, then moment about origin is defined by mu 1 prime, which is expectation of x to the power 1, and which is nothing but equals to expectation of x, which is, being denoted by the letter mu, and whose formula is obviously summation over x, x to the power 1 fx, that is summation over x, x fx. This is the formula for calculating the expectation of x that we have already studied. So in other words, we can say that expectation of the random variable is basically the first moment about the mean. That is called the expectation. Sorry, first moment about the origin. That is called the expectation. Okay. And you observe that first moment about the origin, that is mu 1 prime, this symbol is actually similar to that symbol. So mu 1 prime is actually, according to our chosen symbol, is mu, which is also true for the continuous case also. So similarly, we can think about the continuous case, which will be x fx dx, and which is definitely the formula for the expectation of the random variable. So the first moment about the origin is actually the expectation or mean of the distribution, okay, which happens for r equals to 1. Now I'm going to the next page. When r is equal to 1, the moment about mean is denoted by mu 1, which is expectation of x minus mu, which is calculated as summation of x minus mu to the power 1 fx, or integration over x minus mu fx dx. But if you carefully observe that this quantity, this value would be 0. Why it is so? It is because if we can think of the reason in two ways. First of all, we can directly calculate it. We know some basic properties of expectation. We can write this system as expectation of x minus expectation of mu. And we know since mu is constant and the expectation of any constant is constant, so this would be mu. And again, expectation of x is nothing but mu by symbol, by our choice of symbol. And therefore, this becomes 0. This is one way of thinking. Another way of thinking is that try to carefully look at this expression. What is this? This expression, expectation of x minus mu, is actually giving us deviations, or rather, if I want to write it more specifically, average of deviations taken from mean. That is our quantity expectation of x minus mu. And by definition, it is nothing but sum of deviations taken from mean by total observation. And by definition, this is known from our basic knowledge of statistics that always for any distribution, sum of deviations taken from mean is always 0. So the numerator part becomes 0. And therefore the ultimate result is 0. That is another way of thinking, that first movement about mean is becoming 0. Okay, these results are very important and you just note it down carefully. So this is my first page number 1, take a screenshot. And this is my page number 2, take a screenshot. All these are actually our requirements for studying skewness of a distribution. Okay, so our basic goal is to study the skewness, and these are the prerequisites that I am discussing right now. Okay, when r is equal to 2, then mu r prime becomes mu 2 prime, which is the quantity expectation of x square. And you know that this is in discrete case summation over x square fx, and in continuous case integration over x square fx dx. Fine. And you have already used this particular formula in some problems. This is for discrete case and this is for continuous case. When r equals to 3, mu r prime gives you mu 3 prime, which is similarly expectation of x to the power 3. For discrete case, it is x cube fx. And for continuous case, it is x cube fx dx. This is for discrete case D. This is for continuous case C. For r equals to 4. Now, probably you are thinking that we have understood. Why are you writing so many things? We don't want to we can deduce them by ourselves. So you don't have to write it again and again. I am writing this up to r equal to 4 for some special purpose. So for r equal to 4, it is mu r prime, which is mu 4 prime, which is expectation of x to the power 4. And that is summation over x to the power 4 fx for discrete case, and integration over x to the power 4 fx dx. Up to this, here at this point I'm stopping. Okay, I will write no more expressions. So this is happening for r equals to 1, 2, 3, 4 in case of moment about origin. Moment about origin. What will happen in case of moment about mean? Let's see it on the next page. This is my page 3. So when r is equal to 2, we have mu r is equal to mu 2, which is expectation of x minus mu square, or which is equal to expectation of x minus mu square. But if you carefully observe, you know that expectation of x minus mu square can also be written as expectation of x minus ex, because mu is ex. So we can replace this notation mu by the notation ex. And this is our familiar quantity, which is called variance of x. Okay, so this is the observation, first observation that I'm making. So expectation of x minus mu whole square is actually the variance of x. And we can denote this variance of x, we know, by the symbol sigma square. So basically, the variance of x is actually the second moment about mean. So mu 2. The variance of x is actually mu 2. Also, we know that variance of x e of x minus mu whole square can be simplified in some way. What is that? We can take the square of the term with the formula a minus b whole square. We can write it as x square minus 2 mu x plus mu square. And we can apply expectation on each of these terms. So we'll get expectation of x square minus expectation of 2 mu x plus expectation of mu square. And we know that 2 mu and mu square, they are constants and they can come outside the expectation sign, which I am doing over here. But also mu square is constant, so you know expectation of constant quantity is constant. So therefore it is nothing but mu square, or you can say that I'm taking mu square outside and this becomes mu square into expectation of 1, and expectation of 1 is 1, therefore it is becoming mu square. So we get e of x square minus 2 mu plus mu square, and ex is mu again, so we can put mu over here, and that becomes expectation of x square minus 2 mu square plus mu square, and that is equal to expectation of x square minus mu square. Now, if I use this thing in the formula of mu 2, what do we get? That means what? We can write expectation of x minus mu whole square as expectation of x square minus mu square, and expectation of x square is what? From our previous discussion, expectation of x square is actually mu 2 prime. So we can replace it as mu 2 prime, and we know that mu is similar to mu1 prime as I have shown it in the first page. So we can replace it as mu1 prime. So what we have done over here, I have shown that we can express second moment about mean in terms of the difference of second moment about origin minus square of first moment about origin. Okay, so one particular type of movement can be expressed as with the help of some formula as another type of movement. But I will not write r equal to 3, 4 over here because we will not be needing those things for our purpose of studying Skewness. So now I'm going to talk about why I wrote these quantities. You already know that why I wrote r equals to 2 because I needed to show you this formula. But why I wrote this and that, it is because of the following. We want to study, the motivation of the class is to study the skewness. Skewness means, as I showed you by the diagram, actually skewness can be defined as this lack of symmetry in the curve. Lack of symmetry in the curve. But if I want to quantify skewness with the help of some formula, the quantification formula for skewness would be the following. It would be denoted by alpha 3. This is the symbol, and it is the ratio of first moment about mean. That is when r equals to 3, we get mu3. That is the first moment about mean, third moment about mean. Actually, it is the third moment about mean. Okay, and in the denominator, we'll write the cube of the standard deviation, that is sigma. Remember that if I take the positive square root of the variance, we get standard deviation of x, which we denote by sigma. Okay, but if you at this point you can ask me that we need mu3, that is third moment about mean, then why aren't you showing this third moment by writing this expression? Okay, I could have shown you, but you can do it by yourself. But I am giving you a particular formula, which is if you try to express the third moment, I mean, what would be the third moment? The third moment about mean will be expectation of x minus mu whole cube. So I am not going into the details of this explicit representation. Rather, I am providing you with a formula, which is, I mean, more convenient and can be derived easily by, I mean, if you write the cube formula of this particular expression, you will get a minus b whole cube. If we apply this formula and put the terms, ultimately you are going to get a representation of third moment about mean with respect to the moments about the origin, and it would come, and you have to remember this formula, it would come as the following. It would be mu3 prime minus 3 mu2 prime mu plus 2 mu cube. Okay, and this is the formula for mu3, which we will be calculating and will be substituting in the numerator part of alpha 3. Okay, and sigma, you already know that sigma square is, it is mu2 prime minus mu1 prime whole square. So we will calculate that quantity also. And we will be using these two formulae to calculate the ratio alpha 3 for a certain discrete distribution to study its skewness. Okay. So you just make sure that you are copying these particular pages, or you are taking the screenshot of these pages. Right now we need these two formulae. One is the formula of mu3 and another is the formula for sigma. And we will be needing this formula to measure the skewness. I will start solving the problem in the next class because the time is almost running out. Next class means next session. So after this session ends, you are going to join once again by clicking to the link, and then I'm going to start solving the problem, and with the help of these three formulae that I have discussed in this particular class. Okay, so let's wait for the next session to begin.